Hi everybody, I'm Greg Fishel. Welcome to another bonus weather video in our radar series. And today we're going to be talking about the Doppler effect. And so I just for fun entitled this How Radar Issues Speeding Tickets. Well, in the business of weather, it doesn't, but with cars and police, it does. But anyways, that was just a poor attempt at humor. All right, so let's move on here and talk about wavelength and frequency. And obviously the speed of sound is much slower than the speed of light, but the basic principle is the same. If the car is stationary, whatever sound it is making, like a horn, is going to remain at the same frequency or pitch as it relates to you. So if it's at the same distance from you and you hear that horn honking, then it's going to stay at that same pitch as long as the car isn't moving. Now, the equation relating frequency and wavelength is this. That little symbol to the left of the equal sign is lambda, and that stands for wavelength. The v is the velocity of the wave, so that would be the speed of sound or the speed of light, divided by the frequency. So translating that, wavelength equals speed of the wave over the frequency, which is the number of cycles per second that you're observing with the wave. So, to use the National Weather Service radar example, the wavelength of their pulses is 10 centimeters, which is the same as 0.1 meters. And the wave speed is 3 times 10 to the 8th meters per second, or 186,000 miles per second. So a radar wave moves at the speed of light and not the speed of sound, okay? So if you solve that equation for the frequency, it ends up being the velocity over the wavelength. And if you do that math, you come out with the National Weather Service radar operating at a frequency of 3 gigahertz, which is 3 billion cycles per second. That's just unbelievable if you think about it. All right, so I tried to illustrate this graphically, and I am not the world's best graphic artist in the world, so pardon my shortcomings here. But we have our little human being in the middle, and we have a car off to the left. Now, again, the speed of sound is much less than the speed of light, but the principle here is the same. What I'm trying to illustrate is exactly the same. So as this car approaches this human being, the wavelength is going to shorten. It's going to bunch up, if you will. Okay? So if the wavelength is going down, then the frequency is going up, which means that whatever sound that car is making, the pitch is actually going to go up a little bit with regard to your ears and what you're hearing. And then as it departs you, the wavelengths are going to stretch out. So if the wavelength is getting longer, the frequency is getting smaller, and so the pitch is going to start to go down. And so, if you've ever seen a train go by, you hear that like that, and that's the reason that pitch is lowering, because the wavelength is spreading out as it moves away from you. So here's my poor attempt at this. If the car is moving, the wavelength will shrink and grow behind it. In turn, the frequency will grow ahead of it and drop behind it. And so as the car approaches, the pitch will go up, and as it moves away, it'll go down. So it bunches up, and then as it moves away, you have the longer wavelength and the smaller frequency, and therefore the pitch is lower, and you get that effect. So, by measuring the change in frequency of the object that the radar is tracking, raindrop, snowflake, whatever, the speed of the object away from or toward the radar can be computed. And so that's how Doppler radar works. But there's an interesting caveat here in the sense that the motion that it's detecting is only the motion directly away from or directly toward the radar. That is called radial velocity, and it's something that's very important when you consider looking at a Doppler velocity image. That will be the subject of the next bonus weather video on radar. Okay, folks, that's it for now. You all have a wonderful rest of your Friday, and we'll talk to you soon. See you later.